Let's imagine that we apply the same net force onto two different objects, one with a mass m1, one with a mass m2. So let's apply a force to some object m1. We're going to end up with an acceleration for that object of a1, such that F equals m1 a1. So maybe we've got a mass here, m1, and we calculate some acceleration, or it exhibits some acceleration a1. We apply the same force to a different mass, let's say m2, where we get an acceleration of a2. Now maybe m2 is much larger than m1. a2 will then be smaller, so that the product of the m1 a2 must be the same as m1 a1. If they're the same force, these two things must be equal to each other. And so if m2 is larger, a2 must be smaller for them to equal. If we divide both sides by a2, we can set up a little ratio here of m2 equals a1 over a2 times m1. This is kind of a way that we might think about defining our masses. If we had a single definition for a particular mass, like a 1 kilogram standard, maybe m1 has a mass of exactly 1 kilogram, 1.00000 kilograms. That's our definition of what we mean by a kilogram. Then we could define other masses by applying forces to m1 and then to a different mass, and then we could see, well, what's the differences in the accelerations that we get? And we could use those differences then to determine what the second mass is, basically determining the mass in terms of the first mass. Okay, well, good, that might work. What kind of units are we talking about here for these different quantities? Let's imagine that we have a 1 kilogram mass and we apply a force on it, some force, so that the mass accelerates at an acceleration of 1 meter per second squared. How much force would be required to create this acceleration? Well, F equals ma, so that would be 1 kilogram times 1 meter per second squared. That equals 1 kilogram meter per second squared. Well, this shows us what the units of force are. The units of force here are equal to a kilogram meter per second squared. Anytime I put a quantity in square brackets like this, that means what are the units of it? So the units of force would be a kilogram meter per second squared. That is the standard SI unit, standard SI combination of units for a force. Now this combination is going to be so common that it's got its own name. 1 kilogram meter per second squared is called a Newton. A Newton, obviously after Sir Isaac Newton, is the unit of force, the standard SI unit for force. And we'll write that as 1 capital N for short. Unfortunately, we've only got 26 capital English letters, 26 lowercase English letters, and so eventually we're going to run out of letters for defining different things. So sometimes we use the same letter to represent different things, but hopefully we'll know what we're talking about from context. So in this case, capital N is the unit of force. It's the standard SI unit for force. Anytime you have a mass in kilograms and an acceleration in meters per second squared, you multiply it out, then the units that you'll have for force will be newtons. Okay, very, very good. Let's look at the motion of an object that is falling under the influence of gravity. So the only force we're going to assume that's acting on it is gravity. So after I let go, it falls down, it accelerates downward. We're going to ignore air resistance. So what's happening? Well, here we've got this object, we release it. What do we know? Well, from our study of kinematics, we know from, and also from Galileo's law of falling bodies, it's going to accelerate downward, and the rate of acceleration downward is what we called g. In other words, 9.80 meters per second squared. If the object is accelerating, which we know it is, there must be a force acting on it from Newton's second law, F equals ma. If there's an acceleration, there has to be a force. Well, what's that force? That force is what we call the object's weight. So the force acting on it, let me do that a little bit bigger. The force that's acting on the object must be equal to the weight. How big is that? Well, we know from Newton's second law that the force must be equal to ma, and A is equal to g if it's in free fall, so it must be equal to mg. So the weight of an object, which I'll write just as a capital W, is equal to the mass of the object times g. Now that's very, very interesting. Galileo's law of falling bodies said that all objects, so basically regardless of their weight or regardless of their mass, will fall with the same acceleration. Now this kind of makes sense now if the weight of the object is equal to mg if it's proportional to its mass. Because then what do we have? If the weight is the force that's acting on the object, and if that's the force, mg, and that must equal ma, dividing off the mass, we have the acceleration is always equal to g. Now, we kind of just worked that backwards. We went one way and then just came back exactly the other way. But this kind of makes sense. What this is telling us is that the weight of objects depends on the mass of the object. The larger the mass of the object, the more weight it will have. And it depends on the acceleration due to gravity. Here near the Earth's surface, especially in Atlanta, where it's 9.80 meters per second squared, we multiply by m and we figure out the weight. If you were someplace where the acceleration due to gravity was less, perhaps like on the moon, where the acceleration is only 1/6 about what the acceleration is here, the weight of the object would be less. It would be 1/6 of what it is here near the Earth's surface. The mass would still be the same. Remember, qualitatively, if the mass is a measure of how much stuff there is, well, this ball will have the same amount of stuff, so to speak, here on the Earth than if we take it up on the moon. It's the same ball. It'll have the same amount of stuff. It has the same mass. But the weight here would be less because the acceleration due to gravity would be less. The g would be less. You'd have 1/6 the gravity, 1/6 the weight of the object on the moon. So this is very, very interesting. Object's mass, the mass of an object is independent of where the object is, but an object's weight depends on not only the mass, but it depends on the gravitational acceleration of the object. So an object in a higher gravity would have more weight, in a lower gravity would have less weight. Okay, very, very interesting. Let's take a look at these units just for a second. We've already talked about the SI system with the standard SI unit for mass is the kilogram, and now we have defined the standard SI unit for a force or a weight, which is the Newton. Something that many people in this country are more familiar with is the British or imperial system, where the unit of weight, which is also then a unit of force, is the pound. If you talk about how much does something weigh, you often talk about how many pounds it has or how many pounds it weighs. The unit of mass is a less commonly used quantity, and that is the slug. The standard unit in the imperial or British system is the slug. Now, how do these things relate to each other? Well, in terms of forces, 1 pound is about 4.45 newtons, or 1 newton about 0.225 pounds. So it's a little bit less than 1/4 of a pound. If you're not familiar with newtons, you might think of it that way. If you can think about something that weighs about 1/4 of a pound. Well, if you go to a restaurant and get a 1/4 pounder and you take out the meat, that's supposed to weigh 1/4 of a pound before cooking. After cooking, it'll be somewhat less. I don't know if it's exactly this much, but it'll just give you an idea. If you could just imagine a 1/4 pounder meat patty, that's about a newton of weight. 1 slug corresponds to a weight of about 32.2 pounds on standard with the standard acceleration on the Earth's surface. So slug is a mass, so we're not equating these things, but this much mass would have about this much weight at regular acceleration due to gravity, an average acceleration due to gravity. Okay, all right, great. So we have talked about Newton's first law, Newton's second law. Let's take a look at Newton's third law. Newton's third law of motion is a very commonly stated law, and I bet if I start it, you can finish it. It goes, for every action there is an equal and opposite reaction. Although many people can state this law, it's not always clear exactly what it means. Many people don't really understand it. So let's take a look at it. What does this mean? Every action and reaction, what are we talking about? We're talking about forces. What this is telling us is that if we've got two objects, any objects, so for example, let's imagine we have someone pushing on a box. So the person, we'll call the person object 1, the box we'll call object 2. So what's going on? The person pushes on the box. What does that mean? Person 1 is exerting a force on object 2. So I'm going to draw in that force here. And I'm going to draw this as F sub 2. So this is the force on object 2 from object 1. So I'm going to write this as force F21. So object 1 is exerting a force on object 2. This is then the force, F2 is the force on object 2. And then the second subscript is the fact that it's coming from object 1. Well, what does Newton's third law tell us? For every action there is an equal and opposite reaction. So opposite must mean in the opposite direction, but equal must mean equal in magnitude. We're talking about vectors here. We're talking about two vectors. So if object 1 exerts a vector force on object 2, then object 2 exerts a vector force on object 1 that must be equal in magnitude but opposite in direction. So what this is telling us is that F2 must exert a force on F1. Object 2 must exert a force on object 1. We'll call this force F1, that's the force acting on object 1. And then from object 2, we'll say F12. What Newton's third law says is that these two forces must be equal and opposite. In other words, F12 must equal the negative of F21. And we can put that very simply as a vector equation. The negative sign tells us that these two vectors must have opposite directions, but the fact that the vector equals an opposite of the vector, the magnitudes have to be the same. So what this is saying is that the negative sign tells us opposite direction, but also we know that F12 must equal F21 without the vector sign, because that tells us equal in magnitude. So the negative sign is the opposite part, and equal in magnitude, that's the equal part. Equal and opposite, equal in magnitude, opposite in direction. All right, that's very, very good. Now, this can lead to some confusion. Let's take a look at a somewhat confusing problem. Here we have an artist's rendering of a horse pulling a cart, obviously. What's going on? The horse is pulling the cart, in other words, exerting a force in that direction, pulling the cart that way. What does Newton's third law tell us? If the horse pulls on the cart that way, then the cart must pull on the horse this way. So if the horse pulls on the cart that way with some force, the cart must pull on the horse in the opposite direction with an equal magnitude force. So the question is, how is it possible for the horse to pull the cart and actually move the cart with an acceleration if these two forces are exactly equal and opposite? Is it that this force must get bigger than this one so the horse can pull the cart? What is it? How is it possible for the horse to actually accelerate the cart if these two forces always are equal and opposite? Well, that's a trick question, because if we want to look at the motion of the cart, we must look at only the forces on the cart. We don't look at the forces on the horse. If we want to look at the motion of the horse, then we look at the forces on the horse. These two forces, while yes, they are equal and opposite, are acting on different things. So let's say we want to look at the motion of the cart. Then we look at the forces on the cart. What forces are acting on the cart? Well, we know that the horse is pulling on the cart to the right. What other forces are acting on the cart? Well, it's going to have a weight pulling it down. There's another force from the earth pushing it up, from the ground pushing it up. That's called the normal force. We'll talk more about that later. But the bottom line is that these two balance, so the cart is not moving up and down. There might be some friction on the wheels. As long as there is less friction on the wheels than the force of the horse pulling the cart forward, then what's the cart going to do? It's going to have a net force to the right, and the cart will accelerate to the right. What about the forces on the horse? Well, if we look at the forces on the horse, we do not worry about the forces on the cart. What forces are acting on the horse? Well, yes, there is a force pulling the horse backwards from the cart. That is the force that is from the cart on the horse that is equal and opposite to the force on the cart from the horse. Okay, keeping all that straight. So the cart pulls back on the horse. But that's not the only force acting on the horse. What else is acting on the horse? Well, yeah, there'll be a vertical force, the weight and the normal force pushing up. But what about horizontally? Well, what's the horse doing on the ground? The horse has got to push on the ground with its feet, pushing the earth backwards. Well, if the horse pushes back with its feet, the earth must push forward on the horse. So the friction from the ground is actually creating a force on the horse that's forward. Just imagine if this horse were actually standing on very, very slick ice. Could it exert enough frictional force backwards? Possibly not. Its hooves might just slip on the ice and it wouldn't be able to move the cart in that case. But if it's on nice solid ground with a lot of friction, it can push on the ground backwards with a very strong force, meaning the ground pushes back on the horse with a very strong force forward, as long as this force forward is larger than this force back. It's going to give rise to a net force forward acting on the horse, which means the horse will accelerate forward. And the resultant of all these forces must be the net acceleration of the cart and the net acceleration of the horse should be equal so that they both move off together. Very good. So we've learned something very important here. When we're talking about the motion of a particular object, the motion of the horse or the motion of the cart, whichever, we're talking about the motion of a particular object. You look at the forces that are acting on that object. You might need to look at forces that it's exerting on something else just to figure out what's the force that the something else is exerting on it. But the motion of an object is determined by the forces acting on it, not the forces that it is acting on something else. Okay, good. That's something that we need to keep in mind. Another thing is that when we are looking at the motion of something, a very important part of the problem is to draw a diagram and put in all of the forces that are acting in the problem. In kinematics, we would draw a diagram and put in all of the information about the motion. What's the initial position? What's the initial velocity? What's the final velocity? Something like that. So we would draw diagrams to help us with the problem there. Here, we're going to draw diagrams again. These types of diagrams that involve all of the forces acting on an object or all of the forces acting on another object, these are called free body diagrams. A free body diagram is the kind of diagram that we'll be drawing now anytime we've got force problems. We'll draw in the object and then we'll draw in all of the forces that are acting on the object. Great.